Hello, thank you for joining today's webinar on ruggedized and compact thermal solutions hosted by ACT, Advanced Cooling Technologies, located here in Lancaster, Pennsylvania. If you have a question during the webinar, please use the questions panel in the GoToWebinar program on your screen. It will be submitted to our team and we'll do our best to provide an answer during the last segment of today's presentation. You can also download some great resources that are applicable to our discussion in the same area, so be sure to check those out too. It's my pleasure to introduce you to Greg Heschley, one of our lead engineers in the ACT Product Development Group. Greg is perfectly positioned to speak during today's webinar as he's well-versed in the demands of military and aerospace, and he's worked in a wide range of related thermal management projects. And I am Adam Say, ACT's International Business Development Manager. My role is to manage and grow our international customer partnerships. But no matter where you're located, our sales team is always happy to meet and discuss your project. Please be sure to reach out to us no matter what stage of product development you might be working on. Before I get started, I'll provide a quick overview of ACT. We provide custom thermal solutions based on our experience in advanced thermal systems and two-phase heat transfer technology. When our company was founded in 2003, we focused on thermal management research and development. But since then, we've grown significantly. We have over 220 employees and 140,000 square feet or 13,000 square meters of total space, which is all governed under ISO 9001 and AS 9100D quality management systems. We are proud to be the recipients of many awards, including the 2020 Military and Aerospace Technology Innovators Award, and ACT personnel have also been awarded with more than 60 patents, and we're also the authors of more than 350 scientific publications, although I haven't read all of them, not yet. As I mentioned, ACT offers a complete range of thermal engineering services, so everything from initial design and concept generation to detailed product design, and of course, high volume production. Although our R&D team is working on new innovations every day, we have commercialized many of our thermal solutions and we serve customers in a lot of different markets. For example, ACT solutions have been deployed in a number of different military applications. The military segment has a number of unique requirements that create a number of engineering complications. Thankfully, my colleague here, Greg, and our engineering team are all very well experienced in this field, and actually we're going to discuss a lot of those challenges during today's webinar. ACT also offers technologies that can manage high heat loads for space applications. With our CCHP products, we have over 50 million space flight hours on orbit without failure. And we've also helped resolve thermal challenges for other spacecraft, rovers, and space probes. In fact, the copper water heat pipe high K plates that Greg will talk about in a few minutes also flew on the International Space Station. Very recently, ACT acquired the company TechGuard, which offers custom environmental control systems for extreme conditions. And aside from our military and aerospace customers, we also offer electronics cooling solutions for our industrial market customers. So for today's agenda, we will discuss some of the common environmental conditions for ruggedized solutions, as well as some of the current market trends relating to those environments. In particular, we will discuss the details of two different groups of ACT solutions, including some interesting case studies for each solution set. These solutions are heat pipes and high K or high conductivity plates and phase change material PCM heat sinks. Keep in mind that almost all of our solutions here at ACT are bespoke or custom designed for our customers' applications. And all of our approaches today in the webinar are focused on passive, rugged electronics cooling. Some of these applications might include avionics, radar, embedded computing, communication equipment, signal intelligence, electro-optics, or UAV control electronics. When we're working with applications that are related to rugged defense, performance and durability are always top considerations for our solutions. So to meet these military standards, we need to guarantee that our solutions are corrosion resistant and protected against conditions like dust, rain, humidity, and salt fog. We've also had to design solutions that can withstand rough shock and vibration, G-force or acceleration, as well as certain implications relating to the altitude where the application will be performing. In most cases, we also need to build solutions that are very lightweight, but also meet rugged structural requirements and fit within very tight volume or geometric restrictions. Most of the common thermal challenges that we face in rugged defense applications might include wide ranges in ambient temperatures from maybe -25°C to over 45°C. When heat sink temperatures are applicable, they might have maximum allowed temperatures of 85°C. Of course, we also have to consider the maximum allowed temperatures for the system electronics. These are usually provided by the electronic supplier, but we might see typical values of over 135°C. And if altitude considerations are applicable, we have to calculate solutions that will perform in low ambient temperatures and lower air densities. One of the most common thermal problems that our customers face are conduction limitations. These problems could be rooted from a number of different issues. Perhaps there are localized hotspots on your device due to high heat flux electronics, or maybe there are long distances required to reach your heatsink. Sometimes the heatsink is even remotely located. Aluminum or copper offer relatively good conductivity, but on their own, aluminum is only around 170 watts per meter Kelvin. And although copper has a watt per meter K of around 400, it adds significant weight to the design. So when I hand things over to Greg, he will discuss our high K plate solution, which can actually increase conductivity up to 800 watts per meter K. Another thermal problem that often creates challenges for our customers relates to transient power. Designing to peak power always adds volume, weight, and complexity to a design. And as many systems, such as directed energy or transmit-receive devices, operate on duty cycles, actually, Greg will share more details about PCM phase change material heat sinks, which are excellent solutions for these types of scenarios. So with that, I will hand it over to Greg.
Thanks, Adam. Let's dive into how a heat pipe works so we can understand how to best utilize them in these environments. The heat pipe is comprised of three components: the envelope, the wick, and the working fluid. Because a heat pipe is a vacuum system, the envelope is needed to hermetically seal the heat pipe. It also provides structure for the heat pipe. The wick acts as a capillary pump to pump liquid to the hot spots in the heat pipe. And finally, the working fluid. This is the two-phase fluid that actually transfers the heat from one end of the heat pipe to the other. Let's look at the image in the top here. On the left-hand side is the evaporator, or heat input area of the heat pipe. The liquid in the wick in this area is heated up due to the heat being put into the heat pipe. This causes the liquid to evaporate. The vapor then travels down the middle of the heat pipe and condenses in the colder section on the far right. The capillary action of the wick then pumps the fluid back to the evaporator end of the heat pipe. Because of this pumping action, you can imagine that the amount of fluid that is being transferred is relative to the amount of power that is being put into the heat pipe. Therefore, at some point, the capillary action of the heat pipe is not strong enough to pump enough fluid back to the evaporator. We call that the dry out of the heat pipe. If the heat pipe is working against gravity or against a G load, that can reduce the capacity of the heat pipe, basically limiting the amount of fluid that can be transferred back to the evaporator. So that's one thing we want to keep in mind when we're designing with heat pipes. We also want to think about the evaporator and condenser sizes. We want to maximize those to improve the overall assembly delta T. We'll do an example of this in a couple slides. Next up is a high K or high conductivity plate. High K plates are basically aluminum plates with heat pipes integrated into them to increase the conductivity from the basic aluminum, 167 watts per meter Kelvin for 6061. These can go up somewhere between 500 to 1,000 watts per meter Kelvin, depending upon the geometry. Because most of the frame is still made of aluminum, it has the similar weight and similar strength to aluminum. And we can normally route our heat pipes around critical features so that all of your bosses and mounting holes can be maintained. We also offer a bunch of value add capabilities, including coating, helicoils, and dowel pins, to make this really a turnkey solution for you. Let's take a look at this case study here. Here we have a 4.5U conduction card with 4 90-watt heat loads located in the middle of the card. We have rail temperatures of 60 degrees C in blue on the outside of the cards. We have an overall thickness of 5.5 millimeters, so relatively thin. And because we don't know how this is being oriented in the field, we want to design it to operate in any orientation. So the first thing we like to do is go to the heat pipe calculator on our website, the link above. This asks for 4 inputs, starting with the heat pipe length. We'll make a guess here, but we can figure that out from the geometry pretty easily, starting with the 4.25 inch length. Next up is the evaporator and condenser lengths. The evaporator will be the length of the heat input area at about 1 inch. And the condenser will also be a bit of a guess because we're not really sure of the layout, but let's assume 1 inch for now. Because this heat pipe will probably have some bends in it, the height against gravity that the heat pipe has to pump in the worst case orientation is going to be a little bit less than the overall length. So let's call it 3 inches for now. With those inputs, we output, the calculator outputs this curve. The x-axis of this chart shows the operating temperature of the heat pipe, and the y-axis is the maximum power it can carry before dry out. The different lines represent heat pipes of different diameters, ranging from 3 millimeters up to 1/4 inch. We want to make sure that our operating point is below these lines to ensure that the heat pipe can carry the required power. Assuming that 60 degrees is the operating temperature for the heat pipe, we can see that one heat pipe will not carry the required 90 watts. It's above all of the lines. So we split the power between 2 heat pipes. That gets us a power of 45 watts and gets us to the operating point, that red star. This gives us 3 options for heat pipes: the 5 and 6 millimeter height heat pipe and the 1/4 inch heat pipe. Given that our card thickness is only 5.5 millimeters, we'll probably select the 5 millimeter pipe for this application. That gets us to this design. We integrate 2 heat pipes under each heat load and transfer the heat to the rails. You can see we've tried to extend the heat pipes along the rails to maximize the condenser lengths to increase the overall performance. So we can then take that general layout and import it into an FEA modeling software. So in the image on the left shows the results of this card without any heat pipes. This gives a maximum temperature under those heat loads of about 170 degrees C. So it's pretty hot. Once we implement those 8 heat pipes into this 4U card, that reduces the temperature down to 93 degrees C. So a significant improvement in thermal performance just by adding 8 heat pipes. That kind of shows you a quick example of how heat pipes can be integrated into a card and the performance benefits you can get by doing so. Let's change over to phase change material. Before we dive into the details of designing a PCM heatsink, let's take a look at the basics, starting with the phase change material itself. This material is any material that has a high latent heat value as it changes phase. That can either be the solid to liquid transition or the liquid to gas transition. For most applications, we like to use the solid to liquid transition because the changes in density between those 2 phases are significantly less than the liquid to gas transition. So it's easier to keep it in one compartment. Things to keep in mind when you select a PCM are the melt range. Obviously, you want that to be in a good temperature range for your application. The compatibility with the base metal, normally that's aluminum, but can vary. Type of PCM, the purity, and the capacity. This table shows attributes of a couple common PCM materials, starting with hydrated salts. These can have very high thermal conductivities, which is good, and have high latent heat values as well, but they can be corrosive to most metals and be unstable over repeated thermal cycles. So while they have good properties, they can be hard to actually implement into a rugged and long life device. Next up are metallics. These also have high thermal conductivities, but don't offer as high latent heat, and some of these, especially in the higher temperature range, can be corrosive. So we try to avoid these because they don't provide as high a thermal performance. Lastly is paraffin wax. So these have very high latent heat values and are non-corrosive and stable components, but have very low thermal conductivity. That can mean that designing with them is a bit challenging, but it's normally worth it because of their high thermal performance. So for a phase change material heatsink, as Adam was mentioning, the real use of this is storage for transient heat loads so that you don't have to oversize your heatsink. The challenges, as we were just talking about, is the poor thermal conductivity of paraffin, which can create large gradients during the melt process. So what we need to do when we design a PCM heatsink is properly design the fin pitch and fin thickness in the inside of a heatsink. This is basically a trade study between the delta T going into the PCM and the PCM volume. You can imagine if your fin structure is too big or there are too many fins, you can have really good heat transfer into the PCM, but you've actually removed a good portion of the PCM volume, which reduces the overall performance of the heatsink. So we always have to trade off those two things when we do a PCM heatsink design. Let's take a look at this case study. So here we have the design requirements. We have 10 watts being applied for 110 minutes over this 4-inch by 4-inch area. We have a starting temperature of 60 degrees and a max temperature on the surface of 75 degrees. For this, we have 3 possible PCM materials. And looking at these values here, comparing the densities and latent heats and melt ranges, it can be difficult to figure out which one is going to be the best selection for this. The first one has the highest density, meaning you can pack the most in there, but the lowest latent heat. Whereas the next one is the opposite, the lowest density, but the highest latent heat. The last one is kind of in the middle. So when we get something like this, we always like to start with our PCM calculator. This gives us a good starting point to figure out which PCM is going to be best. So we input the inputs from the previous slide into this calculator, and this gets us a curve that looks like this. Each one of these representing a different PCM. And it's a little hard to see in this chart, but each one of these has a different volume and mass associated with it. So we can compare which one of these provides the best mass and best volume solution. For this case study, we actually ran a transient thermal model for this heatsink. The yellow line represents the temperature of the heatsink as the heat load is applied. As you can see, once the heat load is first applied, the temperature ramps up rapidly before it hits the melt temperature of the PCM. That goes through the long latent heat transition period and then raises it up to the maximum temperature of 75 degrees right near the end. The blue line represents actual experimental results for this same heatsink. As you can see, we are a little bit conservative in our modeling approach, which gives us about a 10% increase in the actual performance compared to the model. That's a good place to be and shows that our modeling is relatively accurate. Lastly, what I want to talk about is how heat pipes and PCM can be combined for the ultimate thermal management solution. If you have a high heat load or concentrated load, or if your PCM volume is somewhat separated from your available or from the heat load, you might need to combine the heat pipes into a PCM heatsink. In this case, the heat load is along the bottom edge of the assembly. The heat pipes are then transferring that heat up and into the PCM assembly where it dissipates the heat into the phase change material. So 4 takeaways for these It's important to understand your thermal requirements and technology options. High K plates are great for spreading and transferring heat using heat pipes. And PCM is great for storing transient loads in a low mass and volume heatsink. Using these two-phase technologies can greatly improve your thermal performance with minimal impact on your assembly.
Okay, Greg, so the first question is, if you have a design temperature requirement such as -25 to 55 degrees C, would a heat pipe be able to meet the full requirement range?
Oh, that's a good one, Adam. So there's a couple different ways that we can solve this problem. Kind of depends on the application. One of them would be to use methanol as the working fluid. That will operate under this entire range. So there won't be any problems there. But most of the time, we actually prefer to use copper water heat pipes still. And basically, because the ambient is so low, even though the water inside of the heat pipe freezes, there's normally enough conduction gradient through the aluminum that's left in a high K card that it'll still meet the system requirements at those low temperatures.
Okay, excellent. The next question, let's see, have heat pipes been used in fighter jet applications? If so, how do you overcome significant G loading?
We do have heat pipes in fighter jets. Again, there's a couple different ways that we approach the solution depending upon the exact requirements. One of the ways is we can shorten up the heat pipes. With the heat pipe short, it means you have less distance against that G loading that you have to pump the liquid. So we can overcome some pretty high G forces by making the heat pipe short. The other way is that because the G loading is normally either not sustained or only in one direction, we can design the heat pipe layout so that it can account for either short durations of those heat pipes not operating, or we have spreading in multiple directions so that we ensure that only one heat pipe is not operating at a time, or at least enough heat pipes are still operating to meet the performance requirements.
Okay, great. The next question is, how many cycles can a PCM heatsink survive before you see performance degradation?
That's an interesting one. We've done testing of our PCM heatsinks up to a couple hundred cycles without any performance degradation. We've also done testing of the PCM itself on a much smaller scale. We've done testing up to a couple, I think it was tens of thousands of cycles for a couple different PCMs. And there is a very minor degradation at that point, but it's really pretty insignificant. And that's a lot of cycles at that point. So in our experience, we really haven't seen much significant degradation up to, tens of thousands of cycles.
The next question is PCM ever integrated with liquid cooling?
We do integrate PCM into liquid cooling systems. That can either be done like right next to the component. And then in that case, in case the liquid cooling system breaks down, the PCM can absorb the heat while the liquid cooling system is booting back up. The other times we've done it where we're trying to absorb some transient loads, some really high transient loads. Typically that's like a direct energy weapon. So some really high short duration loads. And we can then integrate, what we normally do is integrate that PCM into a liquid cooled PCM heatsink so that the liquid cooling is still directly cooling the energy weapon, but we're helping the rest of the cooling system so that it doesn't, require a very large heatsink there. So we're basically reducing the size of the liquid cooling system.
Okay, excellent. Well, I think that is actually our allotted time is just about up. And although we weren't able to make it to all of the questions that were submitted, we will certainly get back to you all by email with those answers. So thanks again for joining today's webinar. Don't forget that our ACT website has a lot of great resources available. Actually, you can also contact us through the website, which is the number 1 dash or hyphen ACT for Advanced Cooling Technologies. So 1-ACT.com. And through that contact form, you can give us more information about your specific application. We'd be happy to set up a call and discuss things in more detail with you. So thanks again for your time today, and we look forward to meeting you all soon. Cheers.